Hey everyone, we will solve the seventh worksheet today. It's about the increasing, decreasing test, critical points, and sketching graphs, and L'Hopital's rule. So here we have a recall first. The first one is about increasing, decreasing test. We know if f prime is greater than 0, then the function f is increasing. And also we know if this function is increasing, then f prime is greater than 0. We have this one too, if f prime, so we have if f prime is less than 0, if and only if f is decreasing on this interval. And this is the first derivative test. So we suppose first C is a critical point. What is a critical point? If we say C is a critical point if f prime C equals to 0, or C makes this derivative undefined. So suppose it's a critical point, then we know f prime changes from plus to negative at this point, this critical point. If this happens, then we say f has a local max at this point. Actually, if we visualize it, so if we have, for example, a function of this form, then this would be C. This would be a local maximum of the function f. And here we have C prime, let's call it C prime. And this will be a local minimum of the function. So we say this function has a local max at C and a local minimum at C prime. And here we have concave upward, the definitions of concave upward and downwards. So if the graph of the given function lies below all of its tangents, we say it's concave downward, as in this figure. So here we have the tangent lines of the function, this, so it's supposed to be tangent. So here we have these lines, tangent lines. So we say we see that the graph of the function is above of these tangent lines. So we say it's concave upward. If we have the reverse condition, we say it's downward. Another recall, we have a concavity test. If f2 prime, so the second derivative of the function, is greater than 0, then its graph is concave upward. If it's negative, if the second derivative is negative, then it's downward. And we say that a point is an inflection point if the function is continuous at that point and its curve changes its concavity. For example, if we have again this graph, we see that this graph is concave downward here from this point, for example A, until here B, and after this B, this point B, it changed its concavity. So this B is called inflection point of the function. And the second derivative test, if f2 prime equals to 0 for some point C, and f prime should be this should be f prime. it's 0 and f2 prime is greater than 0, then it has a local minimum at that point. And the reverse is holds for the point local max. Again, this should be f prime. So we're done with the recall now. Here we have the first question. We're given this graph of the function f of x, okay, on this interval from 0 to 8. So we check first the sign of f prime, okay. So from 0 to 2, we see it's positive, okay, it's above the x-axis, so it's positive. And from 2 to 4, again, it's positive, here we see, right? On this interval, it's always positive, but we need to check if f is increasing or decreasing to determine the sign of f prime now, okay? So we know if it's increasing, then f prime should be positive, and if it's decreasing, f prime should be negative by increasing decreasing test. So we see it's increasing until this point 2, right? So as we wrote here, it's increasing here, then it's decreasing till 4, as in here, and again it's increasing, then it's decreasing after this point 6. So by this test, we see f is increasing on this interval 0, 2, then f prime should be positive. If it's decreasing, we say it's negative, okay? So what about f2 prime, the second derivative of f? We have this concavity test. So we need to check if it's concave downward or upward to say f2 prime is negative or positive. So here we have between 0 and 2, we see it's concave downwards. So it should be, the second derivative of f should be negative. And between 2 and 6, we see it's concave upward. So it is positive. The second derivative of f is positive. And after this point 6, it's concave downward. So it is negative. What about the local minimum and maximum points of f? We see that here we have the table. So we see that it's increasing, decreasing, then increasing and decreasing again. So at this point and this point, which are 2 and 6, right, it has local max. And at this point, which is 4, it has local min, right? So what are the local max and min values of f? We just put, instead of x, 4, 2, and f of 6. Right? As we don't have the formula for the function, we don't know what the values are, but we know as the function has a local minimum at this point, so f of 4 gives us the local minimum value, okay? So what are the inflection points? So here we see that it's concave downward, upward, upward, and downward again. So it changed its concavity at this point, which is 2, and at this point, which is 6. So these are the inflection points of the given function. You can see on the graph too, if you want. We have this question now. For the given function, we will compute these ones. So here we have a polynomial as the given function. So what do? We need to first compute the critical points.
So for that, we need to find the first derivative and equalize it to 0, then find the roots of this function. So you know how to take derivatives. We're given this function, so we take its derivative, first derivative, and equalize it 0, and find the roots 2 and minus 2. Minus 3. So these are the roots of f prime. Now what do? We see that f prime is positive when x is greater than 2. Okay, you can see here if x is greater than 2, this will give us something positive, and this is already positive, so we will have something positive. And for each root we change the sign and get this. So f is then here it's increasing, it's increasing and then decreasing and increasing. Okay, so f is increasing on this interval union to infinity, and decreasing on -3 to, okay, by this test. Now for the second part, what do? We need to compute the local max and min values of f. So we see it has the local max at this point -3 and minimum at 2. So what do? We just compute f of 2 and f of -3 to get the values. So you just put, instead of x, you just plug x equals 2 and get some value. These are easy, so we pass them. And for the last part, what do? We need to find the intervals of concavity and the inflection points. So when we talk about concavity, we need to know the roots of the second derivative of the function. So we take the derivative again. We have already f prime, so we take its derivative. We have this polynomial again, 12x plus 6, and we equalize it to 0 to get the roots of the function, and get -1/2 as the root of f2 prime. So here we have. Now what do? We just check if it's positive or negative when we plug something bigger, something greater than -1/2, and get plus here. You just try it here. Okay, pick some value from this interval. For example, 0 is greater than -1/2, just put here 0 and you get 6. So on this interval, we see that f2 prime is positive. And we have here some root of the function, we change the sign. Okay, if you have some function which is polynomial, you can apply this rule. So each time you see a root of the function, you change the sign. So the second derivative, the concavity test, says that if this second derivative is negative, then the function is concave downward, and if it's positive, it's upward. So the inflection point then is -1/2, right? Because it changes its concavity. Okay, so as we said before, f is concave downward on this interval, which is -∞ -1/2, and it's upward on this interval. So we're done with this function. Now we have sinus x plus cosinus x. Again, we do the same things. First, we take the derivative and equalize it to 0. So the derivative of this function is cosinus x minus sinus x. We equalize it to 0. We get sinus x equals to cosinus x. Then you have this unit circle, right? You have this unit circle, so they are equal at pi/4, and also here, which is
pi plus pi over 4, as we did here, pi plus pi over 4, because it's this pi plus here, which is pi over 4. So the roots are these ones. As we're given this interval, so it means the function is defined on this interval. Okay, so we have these boundaries. Below we have 0, and up above we have 2 pi, and these roots. So what do we do now? We just compute, we just pick some value here, a point here, and see if f prime is positive or negative. So for example, for this point, for this interval 0 pi over 4, we just pick something here, and it will be something here, right? It's less than pi over 4 and greater than 0. So it's something like this. So on this interval from 0 to pi over 4, we see cosinus x is greater than sinus x, right? So that's why cosinus x is greater than sinus x. That's why f prime is positive here. And for each interval, you do the same things and get the sign of the derivative. So what does it say? Now it's increasing in this interval and decreasing and increasing again. So it's increasing on 0 pi over 4 union 5 pi over 4 2 pi, and decreasing on this interval pi over 4 5 pi over 4 by this test. Okay, so it has then local maximum at x equals to pi over 4 and local minimum at x equals to 5 pi over 4. So you just plug x equals to pi over 4 to get the local maximum value, which is you just plug sinus pi over 4 plus cosinus pi over 4. It is square root of x, and you do the same for 5 pi over 4 and get minus square root of 2. Okay, now we need to determine the concavity of the function. To decide that, we need to find the second derivative. So here we have minus sinus x minus cosinus x equals to 0, which gives this equality. So we have, at the end, we have tangent x equals to minus 1. Okay, then when do we have this equality? You do the same things actually. So you have this unit circle. Okay, so you need to have minus 1. Okay, then it means sinus x and cosinus x are equal, but one of them, but the signs of them are different. That's why you get minus here. So either you have here so if you take pi over 4, they both positive. That's why you cannot. Then either we have this angle, which is pi over 2. Here we have pi over 2 plus pi over 4, as we did here, or we need to have this angle, which is this 3 pi over 2 plus pi over 4, which gives you this. So these are the roots of f2 prime. Okay, you again decide the sign of the function of this the second derivative of the function, and by concavity test you have these ones. So what do you say? F is concave downward on this interval from 0 to 3 pi over 4 union this one.
downward, and it's upward on this interval. So the inflection points are these two roots because it changed its concavity. Now we're given the function f of x with this formula. Now actually we do the same things with the previous question, but after doing these parts, we will sketch the graph of the function. So first, again, we find the derivative and equalize it to find the roots. So here we see that f is increasing on this and decreasing on that. So we see they are the critical points, and it has local maximum at this point, which is -2, and minimum at this point 0. So we find so from this, note that f, actually I note it here, so we don't need to now that. So the second derivative of the function, we find it and find the roots. Okay, you know how to compute them, so I don't repeat again and again. So here we have this root, then it's downward, upward, and this is the inflection point, which is -1. So here you see that we compute then. So f is increasing on this interval. So from -infinity to -2, it is increasing, and it is downward, right? It is downward and increasing, then it should be something like this, right? So we write it here. Now, what about after this point? We see between -2, 0, it is decreasing, and it is still downward, right? Till -1, it is downward. So here we have, it is downward and decreasing till -1. This is -1, okay? But let's check if it's 0 actually. So f -1, you put f -1 and get -1 plus 1, -1 -2. So what do we have? We have 0 here. Oh, actually we don't have 0. Let me check again. Okay, it's not 0. We have 5, we have 3, right? Yes, we have 3. Then we erase it. So it is, let me write it, it is 3. Okay, so here we have from this till this -1, we have 3, okay? Then it will change its, remember, its concavity, okay? Here we have plus, negative and plus, so it's downward then upward. So I made a mistake there too, so it is -2, okay? No, it is correct. Okay. Yes, it's correct. So now what do? We know after this point -1 is concave upward, and it is decreasing on this interval from -2 to 0. So still we have this
to the 0, it's, sorry, at 0 it's -1, so we have this. Okay, so after this point 0, we use this to get here. So after -1, we know it's upward, so we have here it will be upward, and it is again increasing on this interval, so we have this. Okay, so here we have the sketch of the function. Now we have this new function, which is x minus sinus x. We find its derivative and equalize it to 0. We see cosine x should be equal to 1, then x equals to 0, 2 pi, or 4 pi. As we have this interval, we have only these roots, 3 roots. We again check if the function, if the derivative of the function is positive or negative. So to find this, we know cosine x, for any angle, it's between -1 and 1. So to get this f prime, we need to first multiply it by minus. So we have here this interval again, and we need to add 1 to get f prime, as I said before. And here we have 1 minus cosine x is between 0 and 2. It means it's positive on this interval, right? So again, you pick some, oh, actually you don't have to do anything. So you see here for any x, it is between 0 and 1, 0 and 2, so it is positive, okay? Actually, as you know, cosinus x is between -1 and 1. You don't have to do all computations. It's almost clear. So f prime is positive here. So the function will be increasing, okay, on this interval from 0 to 4 pi. So here we see it has no local minimum nor maximum because it's always increasing, right? What about the second derivative? We take the derivative of 1 minus cosine x and get sinus x. We equalize it to 0 and see that x should be one of them. So these are the roots of this second derivative, because sinus x is 0 when x is k pi, where k is an integer. So here we have. So here we have the signs. So you just take again the unit circle, okay, to decide the sign of the function. So between 0 and pi, sinus is positive, and between pi and 2 pi, so pi and 2 pi, it's negative, and between 2 pi to 3 pi, again above the x-axis, so it's positive, and then negative. Okay, so we see it. We apply concavity test and get upward, downward, upward, and downward. So these are actually inflection points, which are pi, 2 pi, and 3 pi. So, and also note that f of 0 is 0, right? Here we have 0, we plug x equals to 0, we get 0, okay? To sketch the graph, it will be helpful. And remind that 0, 4 pi is our interval. The function is defined on there, okay? Now, what do we do? Well, let's note again. Upward, downward, upward, downward. And the function is always increasing. We computed it in the first part. and f0 is 0, the function is defined from 0 to 4 pi, okay? So it will be increasing and upward till this point pi. So it will be, it will be like this, okay? You can, f of x is defined by this, x minus sinus x. So you just plug x equals to pi and get of f of pi, which is pi minus sinus pi is 0, so you get pi, okay? So for these points, sinus will be 0, so you will get f of 2 pi equals to 2 pi, and 2 pi, 2 pi. So what about this interval? From pi to 2 pi, it will be again increasing but downward. So on that interval, it will be this. Okay, from that and being increasing, we get this. So what about this part? It will be again upward and increasing. So we have here. And finally, we have this downward and increasing. So we have here. As we had this interval only, as the function is defined on. So we're done with the sketch. Now we have this function. Again, we find its derivative and equalize it to 0 and get 0 and 1 as the roots. Actually, we need to first find its domain. Okay, here we have square root of something, so we need to first check its domain. Okay, we had before something trigonometric and something polynomial, so we didn't have actually this problem, but here we have square root of something, so we need to check first the domain. So x minus x squared should be equal to 0 or greater than 0. Okay, it gives this inequality. So by using this table, you need to have something positive as you have this inequality. So you get 0, 1 as the interval that the function is defined. Okay, so we have this domain 0, 1, the closed interval. Okay, so when we compute the roots, we need to remind that. Okay, so what is f? The roots of f prime that we found before are 0 and 1. They both in the domain, but here you see they make the function undefined. Okay, so and another point, another root of f prime is 3/4. And there's no problem with this point because the denominator is not 0 when we plug x equals to 3/4. So we can take it as a root of f prime, but we will be careful when we have x equals to 0 and x equals to 1. So here we have again f prime positive, negative. You just pick some point from this interval and see if it's positive or negative. So you try that again. So here it is increasing on this interval and decreasing after this 3/4. So now what do? We note that it has local max at this point, 3/4. And f2 prime, we take the second derivative and equalize it to 0 and get this point as the root of f2 prime. But you see it is greater than 1, but the domain is 0, 1. This closed interval. So this is not in the domain, as we noted here. So it's not on the domain, we don't care about it. But we need to decide the sign of f2 prime. So we just pick some point from here and see if it's negative or positive. We see it's negative, so it will be downward, okay? So it will be increasing till 3/4, then decreasing. And on this intervals 0, 1, it will be downward. So let's sketch it. Okay, so it has no inflection point as it's always downward. We didn't say that. So it will be downward until 3/4. It will be increasing, then decreasing. Okay, so we see f0 is 0. We know the domain is between 0 and 1. So here we have 0, 0. Then it will be downward and increasing. So we have here this point, okay, for this first part. Then for this part, from 3/4 to 1, we have this. Let me sketch it again. So here we have this. Okay, suppose it's a curve. So here we have. Okay, it's downward and decreasing. Okay, between this and except that interval, it's increasing and downward. So this is the sketch, and this is the graph of the function. Now we will compute the same things, but we will also find the vertical and horizontal asymptotes. Okay, so here we have this rational function 2x² over x² minus 1. We first note its domain as x² minus 1 is equal to 0 when we plug x equals to plus minus 1. We don't take them as the domain of the function, so we subtract them from the domain. So here we have this r set minus plus minus 1 as the domain of the given function, and note that f of 0 equals to 0 and f of x is 0 if x equals to 0. So the only point that makes f 0 is 0. So this is the only root of the function. Now we need to compute vertical and horizontal asymptotes. First we compute the vertical one. Now x² minus 1 equals to 0 when x equals to plus minus 1. Okay, now we compute the limits. So here we have the limit of the function when x is approaching 1 from right. Okay, here we have this function. We rewrite the denominator as in this form, and we see if we're approaching 1 from from right, we get plus infinity, right? We will something bigger than 1 here, so it will be positive. This is also positive, and this is already positive, so we get something positive here. So it will be infinity, okay? Plus infinity. When we are approaching 1 from left, we get minus infinity. And when we are approaching minus 1 from right, we get minus infinity. And similarly, we get here plus infinity. So x equals to 1 and x equals to minus 1 are the vertical asymptotes of the function as we get infinities. What about the horizontal one? So to compute that, we compute the limits when x is approaching infinity and minus infinity. Here we get 2, and there for minus infinity we get also 2. So y equals to 2 is the horizontal asymptote. Okay, so f prime is equal to, when we find f prime first and equalize it to 0 and get x equals to 0, it is in the domain. Okay, so it's one of the roots of this, it's the only root actually of this derivative. And do the same thing for the second derivative of the function, but see that it has no root, okay, on this domain. Actually, it has no root in real line. So x² cannot be negative when x is a real number, so it has no root. But remark that when we plug plus 1 and minus 1, it
it changed its concavity, its design, so the concavity of the function. Okay, because here we have 3 as power. So when this function, when we plug something greater than 1, this will be positive. So f2 prime will be positive. When we plug something less than 1, it will be negative, as we have the root, the power 3. And we plug something less than -1, it will be again positive. So to decide, to determine the concavity, it will be important. So here we have, as f prime is positive, it will be increasing, increasing, then decreasing, and here upward, downward, downward, and upward. Okay, so what do we do? Here we have this y equals to 2 is horizontal asymptote, and these are vertical asymptotes. So we see when we have something bigger than +1, it will be decreasing and upward. So it should be something like this. Okay. When x is approaching infinity, it will be approaching, the graph will be approaching 2. So it is horizontal asymptote. And when we're approaching 1 from right, it will be plus infinity. So as we did here, so right, here we have +1, so we get plus infinity. And when x is approaching infinity, we get 2, okay? And it is upward, and it is increasing. Sorry, it is decreasing, okay? So what about this part? We do the same things actually. Similarly, we obtain this, okay? Now for this part, from -1 to +1, it is first increasing and downward, so it will be something like this, and decreasing upward, so it will be this, and f of 0 equals to 0, remind that, right? So we have this parabola now. Okay, so as you see again, so here we're approaching -1 from left, and we get minus infinity. So here we have -1 from left. We don't have -1 from right. Sorry, we're approaching -1 from right, and we get minus infinity. And -1 from left, we need to get plus infinity, as we have here. Okay, it's plus infinity. And we're approaching 1 from left, and we need to have minus infinity. 1 from left. So here we have 1 from left, we have minus infinity, and 1 from right, we get plus infinity, as here, okay? And f0 is equal to 0, so we have here 0, okay? And we did before the horizontal asymptotes. So these asymptotes help us to find the graph actually, okay? So this one is, that's all for this part. Let me clear first. Okay. Now we have this function. Again, we have square root of something, so we need to check the domain. It cannot be 0 as it's in the denominator. So this is the domain of the function. Okay, and it's not defined between -1 and 1. Okay, it's not defined on there. So
because it will be negative, that's why, or 0, that's why it's not defined. So what about vertical and horizontal asymptotes? We see the plus minus 1 are the roots of this function. So we check 1 plus. Why do we do that only? Why 1 negative? We don't care about the limit when x is approaching 1 from left, because it's not defined on there, okay? It's not defined on this interval, so we cannot approach 1 from left. That's why we don't compute it. We only compute that. Similarly, we only compute this one too. So we find the limits, okay, as plus and minus infinity. For horizontal asymptotes, what do? We need to compute the limit when x is approaching infinity and negative minus infinity, and we get 1 and minus 1, okay? So these are vertical asymptotes, and y equals to 1 and y equals to minus 1 are horizontal asymptotes, as we found there. So what's the first derivative of the function? We get this. We see it's always negative because it's not defined on this interval, so it will be positive, as we have again positive, something positive here. It's always negative. It means it's decreasing. The function f is decreasing, okay? This has no root, but from the sign of this derivative, we get f is decreasing. And f2 prime, for f2 prime, we find this. So if this is equal to 0, x should be 0, but it's not in the domain, as this is not in the domain. So f has no inflection point then, as it has no roots, okay? But still, minus and plus in 1 change the sign of the second derivative. That's why we again count them, okay? So f prime is always negative, we said before, and f2 prime is plus and negative. Then you can pick again something there and find the sign. So it is always decreasing, and here downward, then upward, okay? So what do we have? We have before computed that the horizontal asymptotes are 1 and minus 1, and vertical ones again 1 and minus 1. Remember, when we are approaching 1 from right, we get plus infinity, as in here, and the limit x is approaching infinity, we need to get 1, as in here. Okay, do the same thing for this part. As the function is not defined on this interval minus 1 and 1, we don't have something here. Okay, the graph of the function looks like this, as it's not defined on this interval. So we're done with this one. Now we will use L'Hopital's rule to find the limits. So we use this rule if both numerator and denominator approach to infinity, or both approach to 0, okay? Unless these case, you cannot use the L'Hopital's rule. So if you put x equals to 1, here you get 0, as in the numerator, and 1 minus 1, you get again 0. So you can approach this rule. So what do? You find the derivatives of both numerator and denominator and take again the limit. So if you take the derivative of the numerator, you get 2x, and denominator, you get 2x minus 1. If you put 1, you get 2 here, and you put 1 here again, 2 minus 1, you get 1, so you get 2 as the limit. So for this part, if we put x equals to 0, sinus 4x is sinus 4 times 0, so sinus 0 is 0, and tangent 0 is again 0. So we can apply the rule. You get the derivatives of each one, so you obtain these ones, okay?
So when you put x equals to 0, you get cosinus 0 here, which is 1, so you get 4. And second squared 5x, which is 1 over cosinus squared 5x, so you get again 1. So at the end, you obtain 4 over 5 as the limit. Now, if you plug again x equals to 0, here you get e to the 0, which is 1. So 1 minus 1 will give you 0. And sinus 0 is again 0. So you both have 0. Then you can apply the rule. Here we have 2e to the 2x over cosinus x. And if you plug x equals to 0, you get 2. Again, we're trying to compute the limits when x is approaching 0, and you both have in the numerator and denominator something approaching infinity. So again, we apply the rule. First, we apply the rule and get 1 over x over 1 over 2 square root of x. So it will give you 2 square root of x over x. If you plug x, not x equals to infinity, but if x is approaching infinity, you get infinity and infinity in the numerator and denominator. So you can again apply the rule, and we take both ones derivatives, so get this one, okay. Then it gives you 1 over square root of x. When x is approaching infinity, you get 0, okay. You can apply the rule as many as you want, but you need to have both infinity or both zeros, okay. So we plug x, don't plug, if x is approaching infinity, we both have infinities, so we apply the rule and get this. You see, you have again the same situation, or so again we apply and then again. So here we have e to the x over 10 over some number which is bigger, so it's not important. So when x is approaching infinity, you get e to the infinity, so it's infinity. Okay. Now we will find the minimum vertical distance between these two parabolas. So for these minimization problems, you need to have a function in terms of only x, okay, or with one variable, I mean, okay. Then you can apply the increase and decreasing test, first derivative test, okay. That's why you need to have some function with one variable only. So here we have, for this problem, we don't have such situation. So we have a function in terms of only x. We don't have any problem there. So this is the distance between these two parabolas. We see it is bigger than that. That's why we first write this, because distance cannot be negative. Okay, it's important. So we have this, we take the derivative and get and equalize it to 0 to get the root. So 1 over 4 is the root for this derivative. So it is, as you can pick again some number from here, this one, for example, so 0 is less than that. For this, you get 0, you get -1, so it's negative, then it's positive. So it will be increasing, it will be decreasing, then increasing. So this is the minimum point. This is local minimum. So it will give you the local minimum value. Okay, so this is the minimum vertical distance between these two parabolas. Okay. Now for this question, we will find the dimensions of a rectangle with this area and whose perimeter is as small as possible. So we need to minimize this perimeter of the rectangle. We first write its perimeter as a function. So here we have a function with two variables, right? X and Y both. So we need to write one of them in terms of the other. So we know this area
and we know it's computed by x times y if we have some rectangle. So we can use this equality to get a function with only one variable. Okay, we just write y equals to 1000 over x. It's not important. You can write x equals to 1000 over y and find a function in terms of only y. Okay, the important thing is to have a function with only one variable. Okay, so here we have this function. We find its derivative and equalize it to 0, get the root, and by first derivative test at this root, this function p has a local minimum. So we found the root of the function. At this point, it has local minimum. Now, what about the other dimension? This and this are two dimensions of the rectangle. So we know y equals to this 1000 over x and x equals to this. So you get that. These are the dimensions of the of such rectangle. Now we have a box, okay, with a square base, so we can denote these edges by x, okay, as we have a square there, and height by h, okay. We need that box have this volume, okay. The volume of the box is given by this formula x squared times h, okay. We know this equality. We will find the dimensions of the box that minimize the amount of material. So to form this box, the material will be used according to the surface of the box, okay? So we need to write the surface area first and minimize it. So what's the surface? So at the base, we have x squared, and for each side we have x times h, and we have four sides of this box, so we have 4xh, and the top of the box is open, so we don't include them. So here we have the surface area. Now, as we have a function with two variables, we need to write one of them in terms of the other. We will use, as you guess, this formula. So from this, we get h equals to this one. And then we have a function in terms of only one term, okay, only x. So we remember we need to minimize it. So we take the derivative and find the roots, okay, so, and find the dimensions. So this gives the minimum, local minimum of the function a. So one of the dimensions is x, which is 40, and for h we use this equality and get 20. So these are the dimensions of the desired box. Now for this one, we have a poster with these with these information. So the top and bottom margins will be of the poster are each 6 centimeter, and side margins will be 4. Okay, so here we have these distances, okay, and the printed material is fixed by this, okay. So we will again find the dimension. So, but we will minimize, okay. What do we minimize? We will minimize this function, which is the parameter of this poster. So here we have x plus 12. Okay, x is in here. So x plus 12 will give you this side of the x plus 12. And this is y plus 4 plus 4, which gives you 8. Okay, so we will so the area, not the parameter, sorry, the area of the poster. Okay, so again we have a function in terms of two variables. We we want to write one of them in terms of the other variable, so we use this information. So the printed material is this is fixed by this. Okay, so we have this equality. So from this part, we will write instead of y 384 over x, okay, as in here. So we have this function and take its derivative and find the roots. Remember, this x denotes the edge of the printed material, so it cannot be negative, so we take only 24. So this function has a local minimum at there. Now we know 24 times y equals to this. Remember, x equals to 24, so we obtain y equals to 16. So the dimensions, which are these ones, y plus 8, which is this, and x plus 12, which is this. So these are the dimensions of the desired poster. Now, I guess this is the last question. So we will find the point on the curve this, y equals to square root of x, that is the closest point to this point, 3, 0. So let's write first the distance, okay, as a function. So here we have 2 points xy and 3, 0. So we write the distance between them as in this form. So we have this function. Now we use this. If this is on the curve, then it should satisfy this equality. So here we have, instead of y, we write square root of x and get this function. Now we have a function in terms of only one variable, which is x. We need to minimize it to get the closest point. So we have d prime as here equals to 0. So this should be equal to 0. So x is 5 over 2. Thus y equals to square root of 5 over 2, because we have this curve. So this is the point which is closest to this point, 3, 0. Okay, as this x, y is on the curve, we can use this equality. That's why we obtain this point. So it's the closest one. So that was the last question. Take care.